I will present, as Anna talked about, a little bit on how we could do more with less, so a little bit of less is more. And the title of it is Tailored Materiality, which is actually also the core of the research that I do in general. So more broadly, it would be tailored materiality research then. And the idea there is to pay close attention to material use and to the ability to control its placement and functional grading in general. Like many of you here, I am somewhere at the intersection of architecture, structure, computation, and fabrication, trying through the projects that I've worked on to find that intersection between these four sectors, and always striving to couple that good geometrical form Francesco was talking about to be materially efficient and use material effectively somehow. And this is very much also the heritage of the places that I've had the opportunity to do research at. Very much of that is, of course, motivated by the two main challenges of our industry at the moment, the environment and digitalization, which in some sense, by trying to address digitalization in construction, we're hoping that maybe it will have some positive repercussions on the environment as well. Of course, it's not the only answer. And in that sense, the focus of the research is on the relationship between geometry, design, fabrication, and construction. We've heard it a lot, that maybe we need to change the way that we design, and we need to change the way that we construct. The link that is always in the room, and that we're always all talking about, but never necessarily as explicitly mentioning, but the link between the two is also fabrication. So somehow my focus very much is on the fabrication side of things. And the promise there is that if we do try to address these 3 points, we have an opportunity to reduce material use, to tailor material properties, to reduce construction waste, and have an opportunity for structural reuse. And of course, the link between these is always somehow found in computational tools or computational pipelines that we're all doing. So in the spirit of paying that close attention to material use and having the ability to control its placement and functional grading, one of the main topics is to develop those kind of tools and pipelines that reliably encode this kind of physical behavior or physical material behavior during fabrication, and combining perhaps various digital manufacturing technologies. Specifically, to get down to the examples, the examples that I want to show are actually ones that are focused on developing construction systems that promote that efficient material use for the construction of complex structures. In this case, it could be concrete, but it could be any other material, so it's really on how we manage to build a particular complex structure. And at the basis of that is the work that I've done in the PhD, where I developed a flexible formwork system that uses 3D knitted textiles as lightweight formworks for complex concrete casting in that sense. The idea there is that we can be lightweight, we can look at producing things fast, trying to reduce waste, and have a way to apply ourselves with minimal intrusion. And that might be in all sorts of cases or different contexts that we're not necessarily used to in a new built-in environment. The main principle of that, I'm going to step out of the way because it's blinding me, is that the way it works is that you start with a design, preferably a structurally informed design, so that we can use less material in the final structure, but it doesn't have to be, I guess. Then for that design, we produce a fitted knitted textile that enables making it. That textile is somehow tensioned in a rig. This could be done with cables, with splines. It could be inflated. It could be done in a number of ways. And very specifically, at the time, it was also coated to make sure that the deflections caused by casting would not be too high. So it's really trying to build that strength up in layers, similarly to 3D printing in some sense. And that makes up your formwork then. There are two main challenges to this, and I'm trying to show that in terms of computational pipelines. So how do we get from the design to the textile that is going to help us make this. That is a communication with machines. And then the second one is, if we do have that, how are we actually going to manage to build the structure with it? And those are two distinct challenges, but they're also two distinct fabrication and computation challenges in that sense. The first example of this, and I keep showing it even though it's an older project, is the Knit Candela prototype. I like showing this one because it shows the first time that we could do this at scale, and it was built in 2018 in Mexico City. As the name might suggest, it's a homage to the famous shell builder, and it looked something like this. In this case, other than trying out the flexible forming system, what we really tried to deal with here is the global complexity of the shape, so having a way to build this in a simpler way than with heavy formworks is the global complexity, but also the local complexity of having a, ooh, that works funny, I'll just point by hand, of having these cavities within the concrete because it's a two-way waffle shell, so you have these kind of ribbed systems. Of course, as I mentioned before, you start with a form finding of a design. This is what the formwork then ends up looking on site, so it's a very lightweight textile that's tensioned into a rig, and even though you might say there's a lot of scaffolding around, there's a lot less than there would be if you had a traditional rigid formwork system. A very important part of that, because it cannot be done in a vacuum, is that coating part, so that we give it an initial stiffness. And in this case, it was done in a very automated way by the specialist Lex Reiter that actually developed the crucial cement-based coating that enables this kind of technology. And it ends up looking something like this. How this ties into simplifying construction is by encoding particular material properties directly during the fabrication process. So what you see here are pockets filled up with balloons. Those are all different size pockets, but they were all the same size balloons. So we don't have, by encoding that directly into the textile, we don't have the problem of going on site and trying to figure out which part needs to go where. It's all the same size that produces different ones. That was then cast with concrete, and then what you get is something that looks like this on the inside and has concrete on the outside. I like to show numbers even though they are cheeky, because we all know they're not necessarily always, there are some caveats to them, but it costs quite little for 50 square meters, but that excludes all the extra scaffolding around that we could possibly reuse. It also only weighed 25 kilos, that's the textile. It took 36 hours to produce, pure machining time. Of course, it took us 2 weeks because we exclude the parts that we did over. And it took 14 weeks from start to finish of the design and the structure standing there, which is promising a particular type of productivity or efficiency, but that comfortably forgets that we don't work 8 hours a day for those 14 weeks, and also comfortably omits the development time before. Of course, all of these things are enabled by pipelines for fabrication. It's not possible to do this if we don't have an automated or a pipeline to talk to our machines so that we can inform that design. It's important to have that communication also with the manufacturers of those machines. Everybody else does it with ABB. I'm doing it with a knitting machine manufacturer in this sense, so that it opens up their sector to a different sector in that sense. They usually do clothing. Now they could be in construction as well. So I see I took a longer time than I wanted to do on that project. The follow-up of that was the Knit Nervi, which we finished last year. And in this case, it's another iteration on this type of lightweight formwork system, but where we try to come a little bit closer to what the industry might also understand as a structure or something that can be applied. It was inspired by the Palazzetto dello Sport, and it's again trying to do this kind of diagrid, but this time with beams that are in shapes that we more easily, readily understand in construction, including reinforcement, because we sometimes still need reinforcement in our structures, and having a reduction of the other support systems that come around. So in this case, the only support systems that were not used in that would not have been used in the final structure are the poles, but they are standard scaffolding poles that would be removed and reused in other projects otherwise. everything else stays in place and becomes an active part of the structure, and that's the layering of it. Specifically to construct this, actually there's a combination of digital and manual craft there, where we put up a nice bending active grid shell that was developed by Lotte, which you've seen just before, measuring and making sure that every little point is exactly where it should be so that we get the grid shell that we wanted. In this case, what we also took advantage of is building the grid shell to begin with, measuring everything because we have those computational pipelines, and then using that for the production of the next step, which is usually not something we can do in construction because we need to start in parallel and freeze the design and make all of those things because otherwise we wouldn't be able to get there at the same time. Again, this is enabled by these kind of computational pipelines for production, and even though it might look the same, there was a development needed there in the sense of scaling those computational pipelines because this structure is 3 times as big as the previous structure that I showed you in terms of surface area and segmentation. So there's another level of fabrication complexity and managing that data or generating those instructions for the machine for something this size. It should have been a video. Ah, yes, there we go. Instead of just 4 parts, there are actually 70 parts to this one, and each one of those has a specific tailored material placement in the sense that it has a very specific pattern that you'll see quite soon. It was easy to assemble, sometimes also alone, most of the time with 2 people. Nicoletta, who's in the audience, was also there helping out. But that makes it a little bit of an easier, lightweight job on site. What you see very specifically here then are these kind of patterns within that surface that are controlled actually whole bit by bit so that you have those densities, and they are controlled for the generation and the production process. Yeah, that was a better image for that. Finally, there is one more project that I wanted to show. The reason is that it's a very good, it's a nice venue to show it because we are in Munich, and it was a good collaboration between TU Munich and TU Braunschweig. It started with, as an inspiration, a small bridge that I did a while ago in the PhD, and we said, let's scale that up and try to make it in a more automated way than all the manual ways that you've seen so far, but also take the opportunity of working with the future generation of engineers and doing that in the context of a teaching workshop. In this case, we took full advantage of the DBFL in Braunschweig and showed all of its capabilities in applying all of the different layers one by one. I'll skip really fast through this because I'm running out of time. But in the end, the message from this one actually was that it was a very good learning process, both because we're trying to have 3 different universities in 2 different countries work together, but also the students that are from civil engineering and architecture working together on learning how all of these technologies come together. And that's actually the value of setting up some of these projects that also bring together technologies made by different people in that sense. Generally, what I tried to do is indeed look at tailored properties, phase-changing materials in upcoming research, biodegradable materials, and reusable ones. I wanted to highlight the group of people that has made my life really nice for the past year in Delft. We work on different topics like simulation, prediction, and design, specifically for the NITs in this case, because as Anas likes to point out, it's not a knowledge gap, it's a knowledge canyon that we're trying to fill in how they behave. On reuse, adaptive systems, and hybrid textiles or deployable systems. In the 1 minute I had left, I wanted to kind of point those out, also because some of them are here, and you might be able to talk to them later on. So Nicole will be presenting her poster later, which is why I don't highlight it. But Anas has been working on trying to predict or calculate specifically how we could build something without having to code it and know how it behaves, which is very valuable. Raitis we've also been working on problems of reuse, and with a nod to Corentin Fouvet, looking at reusing concrete, minimizing the offcuts from those reuse and in double curved surfaces, which also goes into another small project that we've gotten a seed fund for, to reuse wind turbine blades in construction. The reason for it is that all of these usually go to landfill, so we're trying to find that sink of carbon coming back into construction, so taking the waste from one into the other. And in this, it's actually quite complex in the sense that we have a given source, shape S, or a solution space there, and a target T that we need to match. There are computational and fabricational tools and material properties involved in that. So finally, even though I don't have the answer to it, what I always try together with everybody I work with is to address the idea of how we build, who builds, where we build, and what we build. Thank you.